Hello everyone, welcome to another video of the LSA encryption algorithm. In the previous video I explained how the algorithm works. Now I would like to spend a few words to show what are the strengths of this algorithm. I'm not going to explain again how it works, so please if you don't know it and you are curious, go check the first video. Okay, so let's dive into the math. We saw that the algorithm, we have our parties that we called Alice and Bob. We know that Alice sent publicly a ciphertext in the form of a tuple, which is this little c sigma to Bob, where the little c is the element generated by multiplying all the elements of the group up to the chosen element, up to the plain text, modulo n, and sigma is the number of elements congruent to -1 modulo n that Bob will encounter in the decryption before before all the elements have been multiplied together, excluding the last one, the one that is guaranteed by Gauss's generalizations of Wilson's theorem. So this is what goes publicly, all right? Let's analyze this tuple. So this is the only thing that a hacker would have to deal with to hack the message. C is an element of the group generated by a multiplication. Okay, so with this algorithm, once I know the group that I'm working with, then obviously if I am sure obviously of the nature of the group, like what is UN, what N is, then this is very easy to decrypt. However, if I don't know the group that I'm in fact the group, you know that K is a secret and from N goes is generated from K, so UN is secret. Okay, this is secret. And so what I know about C is the C, because UN is a group and the group is as a closure property, we know that C, which is generated by multiplied elements together modulo n, is less than n and coprime with n, because C is an element of the group. So we know that GCD between C and n is equal 1, and also that C is less than n. Okay, this is what I know if I only have this. Now, how many, the question is how many n are such that C is coprime with? Well, infinite, because for each given integer there are an infinite amount of integer greater than C that are coprime with C. So there's an infinite amount of n's to choose from. So C can be a part of any group. To make an example, in the example I gave, numerical example I gave in the explanation, if you remember, we were working with the group U54 and we were sending C, which was equal to 17 and 1. Okay, remember our element was 19, so we multiplied all the elements modulo 54 up to 19, and we had 17. Now this was public. So now how do I really get 17? How do I really get 54 over 17? I say first, 17 is prime, so every integer greater than 17 is coprime with 17. So I can be in U18, in U19, 20, up to 54, but also note that the fact if I have a tuple like this does not mean that my group is small. In fact, first we have the 17, yes, the GCD between 17 and 54 is 1, but also 17 is coprime also with this number here, 6 9 7 5 7 5 7 4 4 2. So are we working on U18, U54, U17, U56, this guy, and this is just a number that I came up with, not necessarily the greatest, so it can be much larger than that. So there is really no this guy doesn't give really any clue of what group we're working with, rather than my n has to be coprime with this. However, we can also disguise this little information, because think that if I am in 54, actually let me state it in general, and then and then I will do an example. Sorry. Still, this is my public. This is the ciphertext. This is public. So the hacker would want to maybe, as we just said, start looking for an integer less than that, coprime with that, to find the group. However, how about Alice sends this? A step back. How about Alice checks, make sure that this element is not in the group? Okay, this element. So Alice checks that C+1 is not in UN. Then she sends this. Okay? At this point, two things are going to happen. Bob doesn't find C+1 in the group in UN. He just doesn't see it. So he knows that there was not a mistake of communication. So he knows that Alice had modified C by adding 1 or subtracting 1. Obviously, both things cannot, for many reasons, cannot be done interchangeably or arbitrarily. And just Alice cannot decide at the moment if to subtract or add. But if we previously agree that if it's possible, Alice adds 1, then Bob knows immediately, in the moment that he doesn't find this element in his group UN, he knows that the element is C automatically. However, the hacker is going to try to find a group. Since I have this, then my group is going to be something that is greater than C+1 and that is coprime with C+1, which is might totally be another group, obviously. In this case, remember that we're looking for, by Gauss's generalizations of Wilson's theorem, to guarantee that the multiplication modulo n of the whole group of all the elements is congruent to -1 mod n, then n must be in the form of p to the t or 2p to the t, where p is prime and t is a positive integer. However, let's exclude, for many reasons, of t being 1. Okay, let's say t is not 1, because this would this trick would not work with any prime, because if every integer is co-prime, any integer less than a prime is co-prime with that prime. So if C is in the group, then also C plus 1, plus 2, C minus 1, they all are in. So if we exclude TB1, then we can use this trick many times arbitrarily. So Alice doesn't have to communicate I am doing it, because simply Bob will not find this in the group. So this is a trick that we found being like pretty and very easy. Let's make a very quick example using the one we already have. Alice is sending C equal 17 and 1, remember, to Bob, and where this was generated in U54, and then instead of this, Alice will send C equal 18 1 to Bob. So 18 is not in U54 because they share a factor 2, obviously. So Bob knows that C equal 18 minus 1, which is equal C 17 and 1. And we'll start decrypting using this tuple. However, if you want to hack the message, you might start trying to find the groups where this element is in, which is coprime with another integer that is surely not 54. Not only that is not 54, but you don't know. So you don't know if Alice did add 1 to 17, so you subtracted 1. So you have to start thinking about all the groups that are coprime, which n is coprime with 17, 18, maybe 16, or maybe they agreed on adding 2 if they previously agreed on adding 2 or 3 or 5 or a prime number to the first part of the tuple, to little c, when it's possible. For each character, each part of the plain text must correspond a tuple. So the process of encryption has to be done for as many symbols are in the plain text. And for all the process, we mean the whole process starting from K. So at each letter, let me space it a little. Sorry, I cannot do it straight. Sorry. If this is my plain text, then this must correspond ciphertext 1, which is in the form little c1, little sigma 1, and this must correspond c2, which is little c2 sigma 2, C3, C4, C5. And think about it. All this, let me state it here, sigma 1, C1, sigma 1, little c2, sigma 2, little c3, sigma 3, little c4, sigma 4, c5, sigma 5. Okay, we started, each of them have been generated by running the algorithm from the beginning. So this element would be an element of UN. This would be an element of something else, let's call it US. This would be an element of UT, UV, UW. Alright? So these tuples are disjoint. They're completely unrelated. They're not consequential. They have nothing to do with each other. This doesn't bring this. This doesn't have any information, does not contain any information about this, about this, about this, about any of them. So in order to decrypt the message, you have to break the algorithm 5 times, because this is repeated and is independent. And remember that each of them, each tuple contains an element that is coprime, that is in an infinite amount of groups. And obviously we cannot use an infinite amount of groups, but I'm going to show you after that even if we use very few groups, then finding the right group is still just a guess. Okay, not only this is part of an infinite amount group, but also we saw, and this is just by experience, is not proven, and I'm just let's say throwing it there. Okay, this is not, but from experience, by running the algorithm over and over and over and over, using small groups from with n2 digits to n10 digits, so with U54, U2000, U up to an n with 10 digits, sigma is always between 0 and 3 included. So sigma is always either 0, 1, 2, and 3. I don't remember if I saw it one time being 4 or someone told me, but it's always very low. So sigma by experience doesn't give any information, and if the group is very small or very large, sigma is always more or less the same. And not only in small groups of 3 with n3 digits, sigma can be full loaded of 3, or and with the group of 10 digits, sigma can be 1. So even in the small range doesn't give any information of the size of the group. One more thing. Assume again we want to send the message hello. All right. How about what's the difference if I send the message A. All these letters, all my A's, okay, they will never be part of the same group, right? So they're going to be 1, 2, 3, 4, 7, 9. There will be 11 different tuples. They have nothing to do with each other. The elements are going to be unrelated. Nothing is going to be no tuple is gonna include informations about other tuples. So my 5 words hello can my 5 letter words, 5 letters word hello might be sent as a 17 long letters word. Since the algorithm is extremely fast because the computer just have to multiply elements together and check the remainder, then I can send literally thousands of characters instead of a couple of characters. But I'm gonna close this video here. Thank you for watching, and stay tuned. I'm gonna show you a few other things in the next videos. Thank you so much.